actually, analog quantum simulation and error correction is pretty weird. So this tutorial is going to be about how to make analog quantum simulation robust a little bit. And it's going to have some questions about what things work, what things don't work. I am not, we have 2 hours. I still think I made too many slides. Not my goal to get through all of them. I'm going to do some whiteboard stuff. I'm just here to answer questions. That's my main goal. OK, good. So just start super basic. So why are we doing, why do we have a robust, why are we trying to do robust quantum simulation? Why are we trying to build these quantum computers at all? So in the real world, we have some kind of quantum system. And then I think people forget that we actually don't know, we don't have an exact description of that thing. We just have some mathematical model, some kind of quantum model, which does the best job we can to describe it. And sometimes we simplify the model, sometimes we make it more complex. And if it's small enough, we just put it on our regular computer, right? We put it on this laptop, we calculate some properties. But those of us who've done classical simulations of molecules and these sort of things, actually how I got into quantum computing was, as an undergrad, I was doing classical calculations of molecules. And I was like, these classical computers are too slow. I need something faster. So I heard about these quantum simulations and quantum computers. So the idea, and I think this is a key piece, which is, the quantum simulator isn't the quantum system. It's a realization of our model. And so when we run that quantum system, we get information about our model, which maybe we cannot calculate on our classical computer. And then, of course, it does give us some information about the quantum system, assuming our model is a faithful representation in some sense. And if we can do all of these things, it's a quantum computer, actually. So if I can build a quantum simulator that can simulate anything, it is equivalent to a quantum computer. There's no difference. All right, so why are quantum simulators, quantum computers noisy? In my lab, we do some theory, some experiments, some computation. I would say experiments are often noisy for really boring things, like your HVAC isn't working, you have noisy electronics. There are many quantum experiments that can measure things like subways. I know of one quantum experiment where they actually replaced a bathroom door. The bathroom door was metal. And when people opened the door, the magnetic field changed. So in the middle of the night, the lab, without any permission from facilities, just replaced it with a wooden door. You can't escape. There's some kind of quantum bath that you're embedded in some system. And then even if you got rid of all those things, the vacuum is a quantum bath, and there'll be vacuum fluctuations. So we have to somehow make it robust to this noise. So my feeling in quantum simulation and information, the whole field, is there's always been this contrast between, I think, Hamiltonian idea and gate idea. So the Hamiltonian idea comes from the physics and says, look, all the dynamics come from Hamiltonians. All the errors come from Hamiltonians. And the way to fix that is to use some sort of quantum control. The other side, the more computer science side, is well, a quantum computer should be made out of operations, these gate operations. And you can think of the errors as unwanted gates. So a lot of times in quantum error correction, people have this model of depolarizing polychannels where you probabilistically add some kind of poly model. And I actually like to think about it as basically there's a devil who is adding instructions to your program. So you've made this perfect program with these perfect instructions, and this devil is like, oh, wouldn't it be great if there was an X gate here? Wouldn't it be great if there was a Y gate here? And then quantum error correction is a way to handle that. OK. So with that in mind, in all of these cases, there are Hamiltonians. So the gates are also Hamiltonians. And the Hamiltonians basically transfer, you could imagine state-to-state evolution, or you could imagine trying to map unitaries between the correct unitary and this failure unitary. And then you have some metric to calculate how these errors, what these errors look like, right? This one is just like a simple average fidelity error. And can someone think of a good example where average fidelity error is like the worst choice of error? Well, we're just in gates here, so like we have the unitary. So if I just have a unitary, it's a good example. So what's again? Polychannel is fine. So polychannel is not a unitary. So I just have two unitaries, and my only metric is this kind of average trace. And my favorite example of where this metric is super bad is like a control, x or z or whatever. Because as n grows, this thing is actually exponentially close to the identity. So if I was only optimizing my unitaries using this metric, I would replace all of my control z's with identity, suffer small error as that thing becomes really large. But of course, you get nonsense answers. And I think that's kind of a cool result. So sorry, this thing killing me. So I'm going to talk a lot about unitary control. So let me just shift this down. I don't know why this thing's off. It's killing me. All right. So I think what's really neat about this thing is that all of our gates are built from these Hamiltonians. And then the strength is that we can actually build the same gate out of very different Hamiltonians integrated over very different time. And a simple example is if on a single qubit I want to do a z rotation, I can do that z rotation directly if I have access to z, or I can do it with only x and y rotations, right? So there are many paths in Hamiltonian space that lead to the same gate. And so when we do a simulation, the way I think about it is our model of the system is some Hamiltonian. Our system has some other Hamiltonian. And our goal is to find some parameterized case of these Hamiltonians such that basically you get out the same unitary. Sometimes you actually don't even care about the unitary at all times. You only care it at like discrete sort of time, sort of flocade time. And then that could make things sort of simpler. Okay. So I wanted to mention that if you have a Hamiltonian which is time independent, then the unitary is just the exponentiation of that Hamiltonian. Easy. If you have a Hamiltonian which is time dependent and it doesn't commute with itself, this part here is basically, I think, a lie. And then I think physicists are super smart, and they're like, the big thing's too complicated to write out, so I'll put this fancy t here. And this fancy t is the time ordering operator, which is like, I'm too lazy to write out what actually happens here. If this Hamiltonian commutes, this thing's exact, and I don't need the t. And if it doesn't commute, this t takes care of all of that for you, right? It's amazing. It's an amazing operator. So yeah, so I'm using it here to make our life easy. All right, so now let's get to work. So we have two Hamiltonians, HA and HB. They both represent some kind of transverse Ising model. We have three types of graphs. We have a 1D graph, a 2D graph, and we have this all-to-all graph. And the question is, what can simulate what? So, so the first question is, on the 1D chain, can HB simulate HA? So talk to your neighbors. Yeah, please talk to your neighbors. We'll talk to your neighbors 30 seconds. If you don't like your neighbors, you can move. Um, okay, so, okay. All in favor of yes? Good, good. Anybody? No? Okay. You in the green shirt? Why yes? Yeah.
If you just set all the BKs to B, then it's the same Hamiltonian.
Exactly. Good. Done. Check. So I'm going to use this less than sign to mean I can simulate this HA with HB. It doesn't mean less than. Everybody happy with this? Okay. All right. So now, okay, yeah, so this one. So now, if HA is on the 2D grid, and HB is on the all-to-all grid, is it possible for HB to simulate HA? Discuss. We're going to have like 10 discussions, so discuss quickly. Yeah. Okay, great. So the question is, what do I mean by simulated on it? And what I mean is, yeah, this, that, so I have U of my target Hamiltonian. What I mean, I'm going to take a very strong simulation term, which is I can make any U of t with U of s of t. I can find some U of s which exactly maps every U of t. That's what I mean. All right. Continue discussing. Are we good? People are happy? All right, so again, yes. 1, 2, 3, 4, 5, 6, 7. No. 1, 2, 3, 4, 5, 6, 7, 8. All right, undecided people, ask me a question.
So can you remind me which one was yes and which one was no?
So yes is simulatable. No, it's not simulatable.
Yes, HB simulatable HA.
Does HB, can I simulate any dynamics of HA with HB? Yeah. All right, yeah, again, there is look to me like 60% of you who didn't vote. So one of you didn't vote, just ask me a question. What is the thing you would need to know? Like, it could be like, I don't believe in time ordering operators. That's fine. I guess nobody wants to admit ignorance on the camera because it's recorded. So we'll go the other way. Yeah. No, we can make these different. But I just want these to be the same. So in the slide here, when I have, say, B of t, J of t, Bk of t, J of t, I apply that I can change them however I would like in time. So, so would someone from the yes crowd like to make the argument why it works?
You have all of the same degrees of freedom plus a few extra, so it should be fine.
Okay, okay. Okay, enough degrees of freedom. Someone from the no side?
We can set J of t to be 0 for the interactions that differ from the all to the just the loop, and so we get dynamics that we like couldn't negate to like make them equal to the loop again.
Yeah, sounds reasonable. Okay, yes side. Okay, so we have two claims. They don't directly, they argue with each other, right? Yes is there's enough degrees of freedom. No is this. These, I don't think, cancel each other out. So someone from the yes side want to cancel this one, someone from the no side want to cancel this one. Yeah.
I'm not exactly sure which one I'm canceling, but I guess like you could like you can flip one of them to try to turn off the Z coupling, like one of the Z couplings temporarily, and then maybe on average try to cancel out the two middle ones. But I couldn't actually work it out to see if it's actually possible or not. So I guess that was like the idea. Was like maybe we could just like flip one of the X's for some period, like break it into like different steps, and on average the middle two cancel out. That's in the maybe crowd, I guess. That's a yes. Okay, cool.
No side?
But you can always just turn off everything or turn on everything. It doesn't really make it just sort of like the J term.
Yeah. So this goes back to this. So when you first look at this, this is right. So I think the answer is yes, and I'll explain why in a second. But the no is a very strong, looks bad, because J is always on all these things. How can I carve this out? So there's all right. So 1,000 years ago, when there were NMR quantum computers, there's this problem. In an NMR, you have all of these spins. And these spins all have random J couplings, Zi, Zj. And they're on all the time. Now you can turn one of these, you can do, if I just have one of these terms, J, I can turn it off. I know when Ani gave his talk earlier, like he talked about anti-commutation, but you can turn it off by basically you can turn it off by applying these X gates. So if I apply an X gate on both sides, it changes the sign of this middle one. Yeah, and if I start to write too small, just yell at me and say it is too small. Right, so this is a super useful trick I use all the time. U of F of M of U dagger equals F of U of M of U dagger. Super useful. I use it all the time. So, so that's great. So I can do this because in this Hamiltonian B, I have complete control of all my x's. So I can turn one x on, one x off, one x on, one x off, as I wish. And if I need to turn all of the j's off, I can turn them off to turn the x on for just a second. And then you could say, well, how am I going to like carve out this 2D grid from this all-to-all connectivity? And so there's an early paper. I don't remember all the authors on these papers. There's an early paper from Debbie Leung and Ike Chuang where they do this in the context of NMR. There's a later paper from Flamia and Biersick where they do it in the context of ion traps. Because ion traps, you have the similar issue that when you try to do an analog simulation in an ion trap, you end up with many different J's. OK, so then this leads to the first question. We're going to work through some more of these examples. But what I want you to keep in mind is this, this simulation. What's going to happen is I'm going to run sorry. So the simulation is kind of weird because it's going to look like a term where I'm running the Ising part. There's going to be some choice of x gates, Ising part, x gates, etc. Whereas HA, I just run HA. So this, and then we're not going to go through how to do it, but obviously there's going to be some cost difference here. And this cost difference is interesting. And then what I want to get to later, I'm holding off the question for now, but what I want you to think about is this is an analog simulation. Is this an analog simulation or no? But anyway, we get to that later. Yeah, any questions? Does that make sense? Does anybody remain in, yeah?
So the way you wrote it on the left board,
Yeah.
looks like the J's can vary on each edge.
They could. What I wanted to say was that this first time I ran into this problem was in the context of NMR. And in NMR, the J's vary on every edge. In our example, J is fixed. We just assume it's fixed over everything.
So you're saying the same quantity by X technique would apply in our situation?
That's right, because it actually doesn't depend on the fact these J's varied. It depends on the fact that I can choose an X1, will cancel all of these Z1, ZKs. And then you basically have to make kind of a binary map, like a Hadamard map, actually, to choose your X pulses, so only the Z's you want to survive. Yeah, which we can go through if people want. Yeah, more.
That sort of implies that you can engineer X to be much stronger than the Ising, where you can use it fast-paced.
Aha, yes, great. So what's my hidden assumption back on this slide? Like, yeah, what have I not talked about at all?
Sorry.
Yeah.
Is that a question? Or
It's a question, yeah. Sorry, it's
oh, the range of the terms?
exactly. So what's missing, when I write this down, if I'm actually going to run this in real life, I should tell you how strong can I make J. I should tell you if it can be positive or negative. I should tell you how quickly I can turn them on or off. But for these like examples we're doing, we assume they're infinitely fast. I can make them infinitely high. I can make them positive. I can make them negative. We just make our lives easy for this morning. Sound good? But it's a great question, right? Because this assumption I made here really is that I can really turn these things on or off. Or in the case of NMR, what's true is that you can make B way stronger than J. And so you can run B in a time where J effectively does nothing. All right, we continue going. What about this guy? The new one. So sorry. So at the end, we're going to look at, I have like A through E. Prepare yourselves. But we're at C. Anything, yeah. All right, so the question was, could we have to make any hard assumptions about B and J? Currently, anything. I'll let B and J be anything. We're just free. Okay, what do we think? All in favor of yes? All in favor of no? No? Okay. So, if this is our definition, the answer is no. Because they don't have this, there's like, these unitaries in that same basis are far away from each other, right? But everybody said yes, which is also what I think. So why yes?
If you prepared in the x basis and measured the x basis on the HCs, the dynamics are the same.
Yeah, so there's a basis transformation which makes the dynamics of A and C the same. And that's the part which is missing in this unitary description, is I got to think about what am I actually preparing and what am I actually measuring. So I like, you know, everyone has their favorite Clifford operator. So my favorite Clifford operator this triangular rotation around the face of the Clifford polyhedron. And it takes, we just set it up in the right way, so y goes to x goes to z, and it's done. So I just apply single qubit. If I have the ability to apply the single qubit Clifford at the beginning and at the end, I get exactly the same simulation. All right. And then, yeah.
Is it not like kind of cheating though to assume that we like have the Hadamard to prepare the
That's
plots at the beginning and the end?
that's a great question, right? So are extra gates for prep and measurement cheating? Yeah, I don't know. I think it's sort of funny. I think what's funny is like I think a lot of times you read a paper where people just accept that this works. Like, oh, it's no problem, I just do this. But if we're being formal, to me it does seem kind of cheating because it's outside of my Hamiltonian, right? I actually have a secret extra part of my Hamiltonian, which I haven't told you about.
And maybe counter question to the cheating, isn't like the basis just made up in our heads anyway? Like the qubits don't know what the basis is till we pick it. So if we like change our basis and we change our basis of measurement, it's just like we've turned our heads in the lab. Which
Yeah.
feels like you can only just like rotate your head 90 degrees.
Change basis, rotate head. Okay. Yeah, so generically I have a very similar philosophy, which is like X, Y, and Z are not given to us by the universe, like we pick, right? I like Z to go up, but anyway.
Also point out that we made the assumption that we could compare the states in the Z basis perfectly to the last Hamiltonian.
That's right.
So it's kind of the same idea, but it is arbitrary.
That's right. So okay, I want to follow up on this. So why do we assume we can prepare in the Z basis?
So can prepare states and then we choose the Z basis.
Yes. That's right. We prepare states, we call it Z. So in some sense, this is back to this, is we just say, okay, we prepare states, we call it X. And then we're done. Yeah?
The question was, can you simulate the first Hamiltonian using the second?
Yeah.
So there is still a relative basis difference. So that unity still needs to be in your toolkit to do that. And so I don't think the basis here, that's the relative difference in basis that matters, not the basis of one or the other.
Yes. So yes. So I guess the way I think about it is, so okay, on the experimental, how many experimentalists do I have? Anybody? 1, 2, 3. Okay, good. Okay. So when you do experiments, what determines the Z basis? First pulse, yeah. When is the first pulse, right? Changes X, Y, Z, etc. Any other things? Quantization axis, right? Quantization axis also missing from this Hamiltonian. To me, what's interesting is almost all quantum systems we use are always in a rotating frame already. We always have taken out the Z basis Hamiltonian because we assume it's already there in terms of the preparation and measurement. But I think it's an important just to remember that we not need, when we think about running a full simulation, we need not only the Hamiltonian, but we need rules about preparation and measurement. That's my main point with this example. Because those Hamiltonians are mathematically the same. They have the same spectrum, they have the same eigenstates, they have the same dynamics. But if I run a calculation, if I run a simulation, they will not give me the same results if I'm forced to only prepare in Z and only measure in Z. And most experiments can only prepare in Z and measure in Z, and everything else is a gate. Does that make sense? I know there are not that many experimentalists, so the theorists, this is your chance to ask those experimentalists a follow-up question on this. Theorists are happy. They like a, yeah. Anyway. Okay, good. Good, okay. Oh no. It's, okay, yeah. Oh, yeah, sorry. Okay, so block sphere, I can say to z, I can say to x, I can say to y. And then I think about this Clifford octahedron, chiral octahedron, actually. But so all single cubic Clifford operations are symmetry elements of this octahedron. And they have to map the points of the octahedron to the points of the octahedron. So Hadamard, so x takes 0 to 1. Hadamard is a rotation around this edge, takes x to z. This one, nobody uses it, which is why I like it. But it basically, you rotate around the center of this face, and it permutes x, y, and z cyclically this way. Okay. Yeah. All right. Okay, yeah, good. Okay, so now we discuss. So the question is, we want to examine, can HD simulate HA? And I'll give people bases. They can change their bases as they like. Can HE simulate HA? And yeah, we discussed briefly. Oh yeah, can we put the Hamiltonians on the front board? Sorry, thank you. Thanks. Yeah, the guy told me I couldn't see what I'm writing on the board on the back. I was like, oh, the slides are up, looks great. Yeah, looks great. Yeah. Well, sorry, say.
In HD, are we summing over only distinct pairs of J and K? Because if we have JK and KJ, those two are close to cancel each other.
JK and KJ commute with each other. Okay, so let's get started. There's a good question about what I meant by this sum. So one possibility is this is z1 x2 plus x1 z2. That's a fun possibility. The other possibility is you imagine, regardless of how high dimensional this graph is, I just draw it on a plane, and then we can make some, and then I shift all qubits so that there's some left-right business, and there's always z1 on the left. If you did that, that's also fine. We can talk about both things. But what do we think? More complicated for sure, I think. That's why I stopped here at E, didn't go further. But what do we think? So we'll start with HD. Do we think we can use HD to simulate HA? Yeah. What's your plan? What's your plan? How am I going to do it? Yeah. So let me run it this way first, okay? So let's assume I meant this. What I can do is this has the y's with zx have the same anti-commutation pattern as x's with the zz's. And so it doesn't matter that this is zx. I can pick some, following Lung and Chuang, I can pick some set of y's in a really harsh way where I'm left with only this. That's super expensive, right? I'm wasting a lot of time resources to get just this one piece. And then once I have this one piece, I use the y to rotate x to z. Minus. But this is very tough. If this is what I meant, I'm actually stuck. Because I can get myself to this single object, but then I don't have a good way to turn off one of these sides. I can only, if I apply the y, it'll change this x to z, and it'll change the z to x. Never gets me back to zz. Does that, okay, yeah, I know that's too much. Please ask questions.
Could you go through the different?
Yes, yes.
The whiteboard on the screen.
Oh, yeah. Yes, can I get the whiteboard on the screen, please? Thank you. And an eraser, hopefully I left it here, great. Okay, so in my Hamiltonian I wrote there's an ambiguity of whether this bond means zx plus xz or if it just means zx. If it just means zx, then we have this property that I can do y pulses. I do some pattern of like j is on, some y's, some j, some y's. And this is about whatever n pulses long. O of n pulses long. It's not so long. And when I do that, I can get out just a single element. So I can get out just j summed over all of these things, so some time, z1, x2. And then once I have this, I can rotate with y to rotate this basically to rotate x to z. So so does that seem good? Great. What's interesting, if this is the situation, you're toast. So you can use this same set of y's, use exactly the same set of y's. There's one other problem, right? You use the same set of y's to get to z1, x2 plus x1, z2. And then I can't fix this, because if I rotate a y, I get zz plus xx or xx minus zz, and I'm stuck. So and so then this is no good. And then there's one trick that I've pulled over everyone's eyes. And what's the other big difference between the sum of zz and the sum of zx? Zz's commute. So this thing is not just the exponentiation. It is the exponentiation of that sum of jz's. But because they don't commute, it's not clear that this process will actually perfectly cancel them out. But I guess it's pretty close. It's close. So these j's have to be, the time has to be this. Basically, let's say j is whatever value it is. J times t has to be small, so I don't have to worry about commutation. This is too tiny. Commutation, great. So that, right, z1, x2, comma, z2, x3 doesn't equal 0. And so in principle, I can do this, but I actually have to go to super tiny time steps. And so this thing becomes O of n times whatever this tiny time step I have to get to is, like 1 over that time step. So it's really painful, really painful. Now for HE, can we switch back to the screen? Thank you. For HE, that's actually a universal Hamiltonian. I can actually make any unitary using trotterization and all these steps. And that means I can actually use HE on even the one-dimensional graph to generate HA on all these graphs, which is crazy, right? So HE, we're basically building a quantum computer. HA is an analog quantum simulator. HD is too complicated. HB, if I map from all to 2D, is that an analog quantum simulator or not? I think we're about to get to the break, but over the break, I want you to think about this question. What's the difference between analog simulation, digital simulation, hybrid analog digital simulation? When you think about when people do experiments on the quantum transverse Ising model, there are a gazillion experiments on the quantum transverse Ising model. I just picked 3. The one is an anti-ferromagnetic Ising model done on ions, where you just turn on the laser with certain frequencies and you get this anti-ferromagnetic piece. But you also have to have the ability to prepare in the plus state. Otherwise, it doesn't work. The one in the center is a 2-dimensional transverse Ising model that does everything in a trotterized way, where there's first the magnetic field, then the ZZ interactions. The ZZ interactions are done in these 3 layers to prevent collisions on these superconducting qubits. And the last one is work by myself and Thomas Bartel and Marco Cetina, and then Chiang was here yesterday. Anyway, he sees me all the time. But here we actually use a tensor network. We try to contract tensor networks on the quantum computer to simulate the system. So just think about these 3 things and where you think they live in the analog versus digital space. Good. And with that, break. Enjoy.
Great. Thank you, everyone. Be back at 10:30.